Okay.
BSc from Ramjas College, Delhi University, then integrated MSc and PhD from Tata Institute of Fundamental Research. Probably his supervisor is a very famous person in string theory, static string theory. And then he joined postdoc at two places. One is Israel and the another is Niger. Niger. And after that, he joined his faculty. Okay. And I think he is teaching here at Tezpur University. So that is.
Thank you, Mozandimai, for the introduction. And thanks to the organizer, for giving me this opportunity to give a talk here. Okay, so so the topic of my talk is quantum chaos. Okay. It's a field of intense research right now. Okay, which intersperse many different fields of physics. Okay, starting from condensed matter, statistical mechanics, and then high energy physics. Okay, and then even quantum computation. Okay, so it's a very interdisciplinary field. Okay, so topic. Okay, I wouldn't say field. Okay, it's a topic. Okay, so for today's talk, I want to I want to dwell on these 3 points. Okay, and I hope that that at least this 3 points you will be able to understand it to some extent. Okay, so I won't be giving a broad overview. Okay, I will concentrate on these 3 points. Okay, the first is, of course, since I am going to explain quantum chaos, I have to explain what is classical chaos. Okay, and as physicists, we cannot say chaos means some randomness, some mass. Okay, we cannot say that. We have to quantify it. Okay, and as a physicist, we have to quantify it. Okay, and we have to be able to measure it. Okay, so first, I will explain classical chaos and how do we measure it. Okay, how do we quantify it? We cannot say, as I was saying, we cannot say that, it's some chaotic thing. Okay, we cannot stop there. Okay, we have to try to quantify it. And let's say we have 2 chaotic systems, we have to be able to say this is more chaotic than this. Okay, of course, saying that both are chaotic, it's sort of kind of easy. But how do I quantify and say that one is more chaotic than the other? Okay, so that's the job of a physicist. Okay, we have to quantify it, and that's what I'm going to dwell on it. That's what I'm going to dwell on in this first point. And I want to, perhaps this is new to many of you. Okay, so I want to explain to you that a single degree of freedom, system, like a harmonic oscillator, a mass attached to a spring which is doing this, or just a pendulum which is hanging and swinging, it is not chaotic. Okay, why is not chaotic? I'm going to explain it in the second point. All right. And in the third point, I'll come to my topic, which is quantum chaos. Okay. And it's a topic of very intense study right now, as I was saying. And actually, it's a source of many discussion, many arguments. Okay, so even in quantum, as we know, as we have learned since the beginning of this conference, as we know, quantum mechanics, the description is in terms of wave function. Okay, it's not in terms of position or not in terms of some observable like position or momentum. Okay. So even the definition of chaos in quantum mechanics is not right now fixed. Okay, so different people actually invent different definitions. Okay, but all of them are so far not 100% 100% good. Okay. So the most well-known definition is in terms of what is called spectral statistics. Okay, it's nothing but just the energy eigenstates of the system. Okay, just like we do, we solve the harmonic oscillator Schrödinger equation. Okay, and we find out this energy level, right? So from that energy levels, there is a way of defining what is quantum chaos. Okay, and that's the most popular one And that's the most widely agreed definition of quantum chaos as of now. Okay. And that's what I'm going to explain. Okay. All right. So I will just concentrate on this 3 topic. Okay. So yeah, chaos in nature, as we know, unlike very, as I was saying, an oscillator which is regularly oscillating, okay, bound state, okay, which is having a finite period and then it's doing this, to and fro motion. Things in life are, very haphazard, very chaotic, okay. And in physics, we want to believe that nature is deterministic, that there are laws and equations governing the system, right? That's actually that's where all those the field of physics started, even the field of science. Okay. So let's say in the system of this, in the solar system, okay, solar system is governed by the Newton's law of gravitation. Okay, it's a very deterministic system. Okay, the force of attraction. Okay, and if you want more precision, you can actually use Einstein's general theory of relativity, which is even more precise. Okay, but for planetary system, actually Newton law is good enough. So we have this very deterministic systems which define, okay, what is the force of attraction between two body, okay, and what is the force of attraction between other body also, and between them, okay, if you have 3 body, okay. But out of this, how does some chaotic behavior, unpredictable behavior arises, okay? That's the field of classical chaos, okay. So in chaos, as I was saying, okay, in classical chaos, we are not saying that everything is so random, okay. The randomness arises from a very deterministic equation, okay. As I was saying, in planetary system, we have only this Newton's law of gravitation and then second law, right? So F equal to ma. And with this, you should be able to solve everything, all the orbit, everything about the planets, right? But I'll come to an example where actually you cannot do it. All right. Yeah. So example of chaos is our unpredictable weather. Okay. Google, as you know, if you look up your phone and you type in weather, okay, Google will be able to predict the weather at most up to the next 7 days. Okay. But they have the most powerful supercomputer in the world. Okay, why can't they predict the weather up to maybe 30 days, or even 1 year, or even the next century? Why can't they do it? Okay, it actually arises. Everything is deterministic, right? How the climate works. It's a fluid dynamic system. You have the temperature. You have the temperature distribution. How the temperature is, how the pressure is. Okay, as of the moment now, and from here, using fluid dynamics, you should be able to predict the weather up to the next century, right? Up to the next 100 years. But, you have a very deterministic system, okay? But somehow, Google cannot predict that, okay? So our weather is actually one of the, very most important example of a classical chaotic system, okay? And actually, trying to predict the weather was when someone, I'll come to that, when someone called Lorentz tried to solve the weather for an extended period of time, okay, actually he discovered this classical chaotic phenomenon, okay. Before that, this classical chaotic phenomenon that I was saying, it was, I would say the modern version, it arises only around 1960s, 70s only, okay. So it's a very new subject, but, it controls our, I'll come to it, okay, it controls our, our life, day-to-day life, okay. And other chaotic system is stock market. And as I was saying, okay, even the 3-body system, 2-body gravitational system, you can solve it very easily, right? You have 2-body, sun and the earth, you can solve it. You'll find by Kepler law, you have the Kepler's law, that the orbit is elliptic and so on, okay. You can predict everything, okay. But you put in another object, let's say Mars or Jupiter, actually you may be able to solve a very approximate orbit, okay, but you cannot solve the orbit exactly, okay. So it might happen that, actually it's well proven, okay. It might happen that if I have this sun, and the earth is revolving, and we have the Jupiter, okay, at some point, all the energy of the Jupiter might be transferred to Earth. The Jupiter, let me draw a bigger Jupiter. All the energy might be transferred to the Earth, okay, and actually Earth might be ejected after some moment, okay, so they will do a lot of revolution. After some point, actually Earth may be ejected away, okay, and Jupiter will orbit, closer to the Sun, okay. So this kind of orbit actually can exist, all right. So Sun, Earth, Jupiter, this tree system, even this simple tree system, okay, we know everything, right? The force of attraction between them. This force, this force, this force we know, okay. But trying to solve it, it's almost impossible, okay. And and as scientists, okay, as I was saying, we try to make sense out of this unpredictability, all right. And since quantum mechanics is the working principle of our nature, okay, we have to study quantum chaos. Okay. And actually, this is something that I have been saying lately, during our college days, we were taught, okay, even us, okay, even very, younger people like us, we were taught that, quantum mechanics controls very small object, and then, general relativity, Newton law, etc., controls bigger objects, okay. But, the last advances in the, last 2, 3, 4 decades has shown that actually quantum mechanics is the ultimate theory, okay. All right, it has to explain even gravity, okay, that's why we have, quantum gravity, okay. So quantum gravity is a field of, very intense research, okay. So everything, okay, including the galaxies, the Earth, the Sun, the Moon, the universe itself has to be explained by quantum mechanics. All right, so, next time someone say, okay, quantum mechanics is for small object and for bigger object, there are other theories, okay. That's with a caveat, okay. The other bigger theory for a bigger objects is they are just approximations. Okay. Ideally, we should be able to explain everything by quantum mechanics. And now, okay, before I dive into the 3 points that I was saying, okay, let me tell you why study quantum chaos. Okay, all right, why study quantum chaos? Okay, it might look like some topic which is not of importance to our day-to-day life. Okay, but it's very important. Okay. As I was saying, there are many systems in physical world, which is almost every system in our physical world are chaotic, okay, and they undergo thermalization, and they have the second law of thermodynamics. Okay, so let me not dwell on it. Okay, let me explain the second point more. Okay, because this is where our real life got impacted. Okay, as Professor Dilip was saying, okay, high TC superconductor. Okay, he was saying that not many people has been able to theorize high TC superconductor, okay. But one of the most promising theory to explain this high TC superconductor is using quantum chaos, okay. All right, it's a very strongly correlated system, okay, and it's very strongly chaotic, okay. So this high TC superconductors, all right, and there is a theory, okay, on the most prominent theory which try to explain this high TC superconductor is a quantum chaotic theory, right? And there are related with that. There are actually, some group are actually very interested in what are called quantum batteries. Okay, and they have a lot of advantage. Okay, compared to our conventional batteries. Okay, as you must have learned, from quantum, computers are more advanced. You have a lot of advantage for some calculation compared to our classical computers. Right. So yeah, let me not dwell on this. Okay, but there are things. Okay, technologies which if we understand quantum chaos in great detail, that will help us a lot. That will make our life much more easier. That will bring a lot of development and advancements, right? And one of the most important one, which is the quantum revolution that is happening right now. Okay, and as I commented, okay, 2 days ago during Professor Zekender's talk, okay. The quantum revolution that is happening right now is we are trying to precisely control quantum entanglement, okay, and quantum actually phenomena. All right. So as I was saying, actually, if I collide these two objects, okay, actually they are two-way function. Entanglement is not like something that happens in a laboratory or and it doesn't happen in our day-to-day life. Okay, it actually happens in our day-to-day every day. Okay, As I'm talking to you, actually your wave function and my wave function, they're entangled, okay? As I collide these two objects, actually the wave function of this object, actually they got entangled, okay? But why this present quantum revolution? Why people are putting in, Google, Microsoft, they're putting in billions of dollars, okay, to try to develop this, quantum computers, okay? It's because they want to precisely control this entanglement, all right? All right. So entanglement is a resource, okay? It's like the coil, it's like the oil that we have, or the iron ore, okay? But to make it useful, we have to be able to control it, right? Turn it into iron, turn it into petrol, diesel, etc. by using refineries, or So the current revolution is an attempt to try to precisely control entanglement, okay, which is freely available. As I was saying, okay, these two go entangled, okay, but we want to control this entanglement, okay. So that's the revolution that's right now happening, okay. And in this revolution, actually, quantum chaos plays a very important role, all right. But yeah, let me go on, okay. Let me not, because I have many things to explain, okay. And as a pure theoretical exercise, okay, physics theory exercise, quantum chaos is actually very important for the resolution of the black hole information paradox, all right. So I think many of you must have heard of black hole information paradox, right? And in trying to resolve this black hole information paradox, okay, quantum chaos plays a very important role, okay, quantum chaos and quantum entanglement. And as part of this resolution of black hole information paradox, it will give us quantum gravity, which I was telling you. And quantum gravity is nothing but, the all important, the holy grail, the theory of everything. All right. And actually, quantum chaos is not just for physicists or experimental, people who want to control high TC superconductors, okay, who want to have a theory for high TC. It actually is it's a subject of interest for mathematicians as a pure pursuit of knowledge. All right. Of course, this might become useful after 100 years, okay. Many of the So one example where this quantum chaos was of interest was by this fellow Terence Tao. I think some of you might know. He is the most famous mathematician of our generation right now who is alive. Okay, he's a genius. Okay, actually, I have attended his talk. Okay, he's very good. Okay, he's a genius. Okay, once in a lifetime kind of mathematician. Okay. And actually, he has interest in this what is called ergodicity. Okay, actually, what Professor Lindian was mentioning. Okay, ergodicity of certain physical for physical systems. Okay, actually, I will come to this. What he is saying, Bumino-based study. Okay, so quantum chaos is a subject of interest. Okay, for all this current current research of many diverse fields in the field of physics, science, as well as mathematics. All right, and let me give you one example. Okay, of Professor Dilip also mentioned about this high TC superconductor. Okay, why we need to explain this high TC superconductor? Okay, it's because we want to control. We want to high TC superconductor has so much advantage that the current that is carried by this big wires. Okay, that same current can be carried by this small strip of whatever this object, all right, which is a superconductor. All right. So if we can find normal room temperature high TC superconductor, okay, then we won't be needing all these big poles, and everything can be transferred in a small strip of this wire. Okay, and there are so many advantages. All right. And let me give you an analogy. This is like our 2G internet, and compared to this is like our present 5G internet. Okay. All right. So let me start my three points that I want to go into some detail. Classical chaos. Okay. And this the most evident phenomena in this classical chaos is, I think you must have heard of this butterfly effect. Okay. It's a phenomenon which says that a butterfly flap it has no power, right? A butterfly flapping, it has no power, but the flapping of the butterfly, its effect might get magnified as time progresses. Okay, that so much so that actually in some part of the the butterfly, let's say flap here, actually it may create a cyclone in some part of the world, okay? Because the effect of this butterfly flapping, okay, its effect might get magnified, okay? Instead of getting, dispersed away, and then, for example, it flap here, okay? And the wind, it will create some wind current here, right? Some current, okay? And ideally, we think that, okay, oh, this current, okay, this wind whirlpool, okay, it might die down, okay? But it might so happen that actually this flapping, the wind whirlpool that it has created, okay, its effect might get magnified, and it may create a cyclone in some part of the world, all right? And this is, this is a prototypical example of a classical chaotic phenomenon, all right? So when there is no butterfly, there is no cyclone, okay? All right? So this is, this is a very popular science kind of topic. So let me go delve into this classical chaos in more detail. One example of this classical chaotic system is what is called this Buminovich stadia. All right? It's like a carom board which includes a rectangle and two semicircles. Okay, it's not, I haven't drawn it as a semicircle, but please, you can think of it as a semicircle, okay? Two semicircles attached to it. And there is a ball which is bouncing back and forth here, okay, inside this. It's just like our carom board, okay? But the only thing is that its shape is like this. Actually, this system is a classically chaotic system, okay? So let me try to explain this, okay? And let me try to, connect it with this butterfly effect, all right? So let's shoot a ball 2 times in this carom board. One time, let's say my red one, the first one. Okay, actually, let me say in words. Okay, the first one I shoot it from here. Okay, it will go here, 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 and so on. And the second time I shoot it a little, displace. Okay, after displacing the initial point. Compared to my earlier red point, okay, I move a little and shoot it again with the same velocity. Everything is same. Okay. Actually, in this, it has been rigorously proven that, or you can actually think of this exercise as 2 non-interacting balls, which they don't collide, meaning they don't collide with each other. You shoot it. Okay, it's just that same identical balls. Okay, you shoot it from here. The only difference between them, you shoot it with the same velocity, same momentum, okay, same angle. The only difference is that one ball is slightly displaced away from the other ball. Very small, okay. Actually, in this carom board, what happens is that as time progresses, as they bounce away from each other, actually their orbit started separating out. Okay, as you can see, this green and the red, as they bounce more and more, okay, they started separating out. Okay, so the last drawing that I am doing here, actually their position is here and the other position is here. All right. So this is from here, actually the definition of classical chaos is defined. All right. It is saying that if I shoot the ball 2 times, but change it, usually this, del Q naught means at time t equal to 0, the initial shooting point, okay. If I change the shooting point a little bit, as time progresses, the position of the ball actually started diverging. Okay, so here, as I was saying, of course, here they are very close, so they will fly very close to each other. Okay, but as time progresses, they started diverging out like this, right? The last one, as I'm saying, is very diverse. Okay. And the most important point about this is that the divergence is actually exponential as a function of the time. Okay, here, the number of bouncing. All right. So as time progresses, although they started only very slightly different, okay, as time progresses, they become very separated out, and they started doing all sort of random thing, okay, although they started almost same trajectory. All right. So this is the this is the prototypical definition of classical chaos. All right. And this lambda, the exponent of this divergence as time progresses, is called the Lyapunov exponent. All right. And people have discovered, including mathematicians, okay, discovered many examples of chaotic system This one is actually the first one discovered was the Sinai billiards. Okay, this is just again a carom board, but the carom board look like this. It's a rectangle, but out of this you put in another boundary. Okay, so the ball can bounce only in this region. Okay, and you can show that actually, if you started from 2 points which are close to each other, shoot 2 balls which are non-interacting. You don't let them collide. Okay, of course, if they collide, then things will be different. Okay, then actually their trajectory will diverge. Okay, and one example. Okay, is other example is double pendulum. All right, double pendulum is, as you know, just 2 pendulum, one and another attached here. It has been shown that this system is also chaotic. All right, in the large energy region. Of course, if you do a small oscillation, let them hang, okay, and then do a small oscillation, then you can do your usual, harmonic oscillator approximation, right? Remember, in your exact pendulum, we can do expansion of the sine theta, and then we get our usual harmonic oscillator, right? But this happened, the chaotic feature of this pendulum, okay, it actually start happening when you have some violent oscillations, right? And actually there are circuit systems. Okay, people have actually invented like these circuits, which are nothing but some circuit which is constructed out of inductor, capacitance, and resistor, and they show chaotic behavior, meaning that their output voltage show chaotic behavior. All right, and in general, in many almost all non-interacting, almost interacting non-linearly interacting many-body system, they are almost all of them are chaotic. All right, and in here actually I haven't discussed the exact pendulum. Okay, it's because it concerns my next topic. The exact pendulum. Remember, the exact pendulum is the equation looks somewhat like this, right? So let's say the pendulum displacement, I call it some theta. The exact pendulum equation is this. Some constant, let me call it k, is g over L or something, okay? But let's just call it some constant k. And then we have sine of theta equal to 0, right? And you might have been told that actually this cannot be solved, okay? But actually this can be solved, okay? It can be solved exactly. And it's, it can be exactly solved in terms of what is called the Jacobi elliptic functions, okay? And actually, the pendulum is a periodic motion. Right? It's just that, unlike our simple harmonic oscillator, in which the period of oscillation does not depend upon the amplitude, the period of this exact pendulum oscillation, it depends upon the amplitude, okay? So it's just a more complicated system, but it's exactly solvable. Yeah, and as I was saying, okay, I am saying interchangeably these two words, okay? A system which is chaotic, I would say that we cannot solve it exactly, okay? Analytic solutions, just like for example for our harmonic oscillator, we can solve it exactly, right? This harmonic oscillator, the equation is x double dot is equal to plus omega square x, right? And its solution is nothing but in terms of as a function of time, it is some amplitude times some cos of omega t, cos or sine, okay, and then phase factor phi, right? So when I can write something like this, we say that the problem is exactly solvable. And this kind of exactly solvable problems, they never are chaotic, okay, the chaotic definition that I was saying. All right? So, yeah. So the reason why I was saying that even this exact pendulum, which we are told that this cannot be solved exactly, so that's why we have to use the approximation, right? So I think we are said that sine of theta at small angle of sine, it starts with theta and theta minus cube and 3 factorial and so on. So when this oscillation is very small, we can approximate it by only theta only. So this sine theta can be replaced by theta. So this reduced to this equation, and then we can solve it, right? So, but this can be exactly solved, okay, and this is not chaotic, okay. And let me give you a reason why. Actually, many systems which have, all systems which has only 1 degree of freedom can be, does not show any chaotic behavior, okay. So that's my topic, okay, second topic, which actually I was saying in the beginning of this, in my talk, okay. So I'm coming now to this second point. So, yeah, okay, let me briefly stop here, and if anyone has any question, please tell me.
you have this kind of trajectory, right? Though these systems are not interacting to one another, there may be cases where when the particle bounces to the boundary, it may lose certain energy or something like that.
No. Actually, this is a sort of a thought experiment. We say that it's everything is elastic. Yeah, everything is fully elastic. Yeah, even if there is energy loss, the problem will be even more complex, and it will be even harder to solve. Okay.
But that's fine for the pendulum. So even if it's 1 degree of freedom, if you introduce the damping as a perturbation to the system, would it be a kind of chaotic system, or would it be?
Yes. Okay. Very good question. I'll come to that. So then, any other questions? Okay. So I'll come to my second point. Okay, why no? Like I was saying, this pendulum, the exact one. Okay, with no friction assumption. Okay, any system like this, they are never chaotic. Okay, so I'll explain that. Okay, so as you can see, a pendulum just swinging in one direction like this, it has only 1 degree of freedom, right? This angle. Of course, a particle in 3 dimensions, it has 3 degrees of freedom, x, y, z. But the pendulum, which we let it swing, okay, just for our simplicity, we let it swing in the plane, it has only 1 degree of freedom. Or this spring, which is doing only this motion, it has only this 1 degree of motion, which is this displacement, right? Only in one direction. Of course, we can discuss harmonic oscillator, which has other direction. Let's say this displacement, also this y, okay. Then things become more complicated, okay? But when I say a system of only 1 single degree of freedom, I mean it has only 1 displacement, like this, okay? Only 1 function of time, okay? Not 2 functions. Here, if I have this y, then this y also will be a function of time, right? So I have only 1 function of time, okay? I think the displacement is the best, explanation. Best word for this degree of freedom. So, sorry. Actually, okay. Before that, okay, let me go back to the history a bit. Okay, so as I was saying, this fellow Edward Norton Lawrence, okay, he discovered the modern chaotic theory only in 1961. All right. And he is usually known as the founder of the modern, okay. Actually, some similar system were studied by Poincaré, okay, long way back, okay, more than a century back, okay. But his way of studying, okay, is not, it's slightly different, okay. So the present way we are studying, okay, it all started, okay, the renewal of this renewed interest in this chaotic system is because of the work of this fellow, okay. And so. As I was saying, it all started with this, when he was trying to actually simulate a weather system, all right? So what was he doing? Okay. He was trying to, simulate a weather system by considering some variable. Here it was mentioned 12 variables, okay? Temperature, pressure, wind speed, humidity, and so on, okay? Some 12 variable, using this 12 variable, he put it in a theory of some hydrodynamic equation, okay? And he let the equation evolve in time, okay, and he is trying to find out what is the final value of the pressure, temperature, and so on, right? That's how we predict weather, right? Actually, that's how even the Google predict our weather that we look at in our phone, okay? So they measure the current temperature, pressure, humidity, and so on. They have a model of hydrodynamic model of our weather system. They put it in. They let it evolve in time, 1 day, 2 day, 3 day. And they look at what is the temperature at that, 1 day away, 2 day away, 3 day away. And, whatever the number they printed out, they put it up in their website, and we look at it and we think that it is true. It's going to be true, okay? But it's not always true, okay? It's because of classical chaos, okay? So Lorentz, he was trying to do the same thing, okay? But, at those times, the computer were very slow. So actually, to fasten it, he do something, okay? That he wanted to see a sequence of data, but to save time, he started the simulation in the middle of the course, okay? Okay. So let's say he was trying some simulation. He studied it, he let it print out, okay, and look at the printout. And then let's say let me give you an example, okay? Let's say he was trying to predict for 2 days, 2 consecutive days, 1 day, 2 day. So for 1 day, he predict, and he have a print. At those time, there were no screen, etc. So he look at the printout of this the final temperature after 1 day, okay? And to save time, he didn't start it again from the day 0 and do two time evolution, okay? 2 day evolution. He used this one time print, and then he feed it again in his model, and then he evolved it one more, and then he think that final time, that final temperature, pressure, that should be the correct result after 2 days. So 1 day and 2 days. He think that that's true, okay? But something weird was happening, okay? That, as usual, in our computer, our computer right now, single precision, double precision, they have precision up to 16 digits, right? But usually in our printout, we are given only 3-4 digits, right? So his printer, although the computer works at 16-digit precision, his printer print out only three numbers, okay? So the computer was actually the computer was running this number, okay, after the first day, okay. But the printer, the printout that he was getting, it prints out only this number, okay. And so actually he feed in this number again, he do one more 1 day evolution, and he got a new temperature, pressure, okay. That's the expected, weather after 2 days, right? But just to check again, what he do is he start from this same value, okay, from the 0 day, and do the full 2 day evolution. All right. So he do 2 numerical experiment. The first one is 1 day evolution, print it out, look at the number, type in that number again, do one more evolution. That gives after 2 days some temperature, pressure, okay. But he do again one more in which he do the full 2 evolution, no printout, okay. What happens is that these 2 experiments give very, very different results. Okay, so that's what he's saying. So in one, you started, okay, and you let the computer do his calculation with this full 3-digit precision calculation. He let it do fully, and it gives out some temperature, pressure after 2 days. But the second one, he was doing, this is very important. That's why I'm dwelling on this a little bit. I'm taking some time. The second one, he took a printout and type it instead of this 6-digit number which the computer works in, he put in only 3-digit number. Okay, but this number is very small, right? But this very small difference actually it creates the big difference in the evolution of the 2 days. All right, so it's very similar. Okay, so as he is saying here, this difference is tiny. What he is doing is he is just forgetting this 3 number, okay, 0, 0, 0, 1, 2, 3. Okay, but this small difference, okay, it gives rise to this small difference in the initial condition. It gives rise to a large change in the long-term region. Okay, so it's very similar to what I was saying here. Okay, you started out with a very small difference. Okay, but as time progresses, the trajectory started diverging. Okay, exponentially. This is very important. Okay, exponential divergence. If it is not exponential, actually we say that the system is not chaotic. All right, so in his word, chaos is when the present determines the future. As I was saying, as a physicist, our job is to, we try to explain everything. We try to have full control over everything, all the system that we have in our hand. Okay, but even if we have all this deterministic law and equations like this, okay. By the way, for this double pendulum, you can write down the equation of double pendulum, right? It's very easy, okay? It's just a 2 equation for, let's say, some angle theta and another angle theta 1. Theta 1 and theta 2, okay? It's just 2 couple differential equations, all right? So it's a very, very deterministic system. The equation is there. We can actually solve it, okay? But the problem is, it's a deterministic system, okay? In which the present predicts the future, but the approximate present does not approximately determine the future. Okay. So for example, if, as I was saying, why does Google cannot predict up to let's say 30 days away or 100 days away or even a century away? It's because the measurement that we are doing, okay, the temperature measurement, for example, look at the best thermometer actually the best thermometer can only measure up to 6 digits or something, all right? So there's always a lot of error, okay, when we measure this experiment and put it in the, type it in the computer to solve the equation of the weather, okay. So that error, which cannot be avoided, because we have a thermometer which can only up to some digit, right? That error actually creates the unpredictably like what I was explaining. All right. So he concisely, in his word, okay, chaos means this. Okay. And I think this is a very concise statement of what is a classical chaotic system. All right. And as I was saying, this is why Google can show only weather up to the only for next 7-8 days. Okay. Even with their best supercomputer and all, okay, they cannot predict the weather system up to the next 30 days or even the 30 days they cannot predict, okay. All right. And opposite of this chaotic system where actually things are very, things will be very haphazard. There are, one example of a very solvable system is actually a ball bouncing in a spherical carom board, okay, circular carom board, okay. Actually, it's the orbits are, trajectories are very highly irregular, okay. Yeah. So let me come to my second point. What I was trying to come to, that chaos is only possible for a system of degrees of freedom more than one. All right. If you have only 1 degree of freedom, there cannot be no chaos. Okay. So degree of freedom of just one single degree of freedom system are, as I was saying, the simple harmonic oscillator or the exact pendulum and so many other. Okay, you can construct. Okay. The reason is that the phase space. Okay, the phase space of this single degree of freedom, it will be 2-dimensional, right? You will have the position and you will have the momenta. This is what we call the phase space, right? Not the configuration space. Configuration space will only have this in the x part, position part. So for a single degree of freedom system, the phase space is 2-dimensional. Okay. And actually, by common sense as well as there has been theorem which says that, and by the way, this is the trajectory of a harmonic oscillator. Okay, in the harmonic oscillator, as the object is bouncing back and forth, right? So the object is in x position, it will be going. This will be for different energy. Okay, let's say for the low energy this orbit. Okay, the harmonic oscillator will be doing this small oscillation, and as we know, at this extreme point, its momenta is 0, right? So that's why the momenta goes down to 0 here, and then the momenta goes to negative maximum, and so on, right? So this is how, this is the phase diagram of a harmonic oscillator. Okay, is it? I think it's clear, right? Since we are all physicists. Okay. So as I was saying, the phase space of a single degree of freedom is 2-dimensional. Okay, and in classical physics, there has been rigorous theorem as well as by common sense. There is a principle or a notion which says that trajectories, okay, lines of motion of this object in this phase space, they cannot intersect. All right, it cannot be like this. So let's say, let me do even for a complicated system. I'm showing here an elliptical system. Okay, the orbit for a simple harmonic oscillator is very simple. It's elliptic, but for some weird system, it could have been like this. Okay, P is here, X is here. All right. But there is a theorem which says that in the phase space, trajectories cannot cross. Okay, so I cannot have a new trajectory like this. It's because, let's say, I start from here, okay? Let's say I start from here and I do this motion, okay? It's kind of some simple harmonic oscillator, but a very, with some random force here and there, okay? And it come back here, okay? It come back here, and as it reach here, since it has the same initial position and momenta, it actually has to go in this direction, okay? It cannot start a new trajectory, right? It makes sense, right? Because the initial condition and the initial position and the position and momenta are the same, so it has to go here. Okay. So in classical physics, trajectories cannot cross each other. All right. So that's why for a system of single degree of freedom, since its phase space is only 2 dimension, even if it do a bounded motion, it has to always come back to the same point, and then it will have a regular motion. Okay. So this is for the simple harmonic oscillator, right? Where at the maximum point, x point, the momenta is 0, and at this equilibrium point, the momenta is maximum, or here. Okay. Because this negative will be the direction. Okay. And so on. So the simple harmonic oscillator is doing this. Faster here, slow down, faster here, slow down, faster here, slow down, and so on. Okay. So I may try to invent a very complicated simple harmonic oscillator which may have a trajectory like this. But because the phase space is 2-dimensional, it has to always come back to the initial point. Okay. So that's why the trajectory of a single degree of freedom oscillator, this system of single degree of freedom, it is always a periodic motion. Okay. Of course, I'm considering a bounded system in which the particles don't fly away to infinity. Okay. So this is why. Okay. But now consider, let's say, the double pendulum. Now the double pendulum has 2 degrees of freedom. Let's say this angle θ1 and this angle θ2. Okay. What is the phase space of this two degree of freedom system? How many dimensions? 4, right? Now in 4 dimension, you have the extent. So for example, consider here. Okay, if I have another extension here, the trajectory, as I was saying, in 2 dimension, it has to always come back here. Okay, but if I have another dimension here, it might go away and then travel away like this and do all sort of this thing, right? Because I have another dimension in which things can go. And that's exactly what's happening in the double pendulum system. Because this has 2 degrees of freedom and its phase space is 4-dimensional. 2 position, 2 momenta. So it's a 4-dimensional phase space. That's why it can have all kinds of chaotic motion, okay? And its trajectory may never come back to its initial point. All right? And that's why, a system of single degree of freedom cannot have a chaotic dynamics. It can have only regular dynamics. And if you have more than 2 degrees of freedom, it can have chaos. Okay. Yeah, as I was saying, the trajectories do not cross. So in 2-dimensional phase space, okay, this is what I was trying to explain. Yeah. So coming to Tamarake's question. Yeah, so if you have friction, okay, actually you can have. And the simplest example, okay, that people study as a chaotic system is just a single degree of freedom like that, just a pendulum. But you put in extra forces, like you kick it periodically. It's called driven system, okay. It's a very, very, floquet dynamics, okay. This, I think it's a subject of study, intensive study by quantum matter, condensed matter theory people. Okay. So even for this, even as I was saying, a pendulum which is just a 1 degree of freedom system, it doesn't show chaos. Okay. But if you drive it, if you let's say if you're using a hammer, you hit it periodically. Okay. Then actually this pendulum, kick pendulum, actually it has been shown that it's a chaotic system. All right. So it's when you bring in other forces, then of course, even the single degree of freedom system, it can have chaotic behavior. Okay. And actually this kind of kick system, kick-driven system, 1 dimension, they are usually called 1.5 degree of freedom system. Yeah. Actually, you can Google it. Okay, and many people say use this terminology, 1.5 degree of freedom system, because you have some external driving. Okay. So I think I have answered your question. Yeah. Yeah, so this is what I was saying. Right now, as we know, quantum mechanics is the pinnacle of our understanding of the physical world. I'm from a high energy physics, string theory background. So as I was saying, we have decided that everything has to be explained by quantum mechanics. Okay. Yeah, this is what I was saying. Okay, and so we have to study chaos in quantum mechanics. Okay, a lot of progress has been made, but still many things are unknown. Okay. Even the definition of quantum chaos is not settled.
Yeah, so
Yeah.
Quantum mechanics, as we know, that the Schrodinger equation is linear.
Yes.
But chaos essentially means that it has to be associated with nonlinear dynamics.
Yes.
So how do you explain quantum chaos?
Quantum chaos, yeah. So actually, as I was saying here, even the definition is not settled. Okay. So many people invented many definitions. Okay. So and actually, this is a field of interest for, as I was saying, for mathematicians also. Okay. How classical chaos? As I was saying, as I was explaining here, all this classical chaos system, it should arise from quantum mechanics, right? Because as I was saying, quantum mechanics is the fundamental theory of our physical world. Okay. How does quantum classical chaos arise from quantum mechanics? It's actually a study of intense research. Okay. So many people have invented, as I was saying, okay, many people have invented, and the reason why we cannot define quantum chaos is because for example, in the definition of classical chaos, I was using these positions, right? Position as a function of time, as a function of the change in the initial points. Okay. But in quantum mechanics, we don't have positions and momenta because they are just observable. You do a measurement, and then the wave function will collapse, and so on and so forth. So a lot of complication arises. Okay. So we should try to define classical chaos in terms of the wave function. Okay. So that's the main problem. Okay. So many people have invented many techniques to analyze classical quantum chaos, and one of the example, the most well settled, okay, diagnostic. Okay, so we call them diagnostic of quantum chaos because just like diagnostic of some disease or something. Okay, they are the tools. Okay, theoretical tools to check whether there is quantum chaos and to what extent the system is chaotic. Okay, so this is very important. Okay, you might say that two systems are chaotic. Okay, as I was saying in the beginning, you might say that two systems are chaotic. Okay, but as a physicist, we should be able to quantify it. Okay, we should be able to say that this is more chaotic than this. All right, and actually for quantum chaos, by the way, classical chaos, by the way, this Lyapunov exponent is the quantifier. This lambda. If this lambda is large, we say that the system is more chaotic. Okay. So yeah. So many people try inventing many tools to diagnose quantum chaos and to measure quantum chaos, to what extent the system is chaotic. Okay. And the best known one is this spectral statistics. Okay. And recently there has been a lot of proposals like operator scrambling, out of time order correlations, spectral form factor, and many complexities. Okay. The idea of this quantum chaos actually is very closely tied with the quantum computations. Okay. It can be talked in terms of the progress, the divergence of the trajectory in classical systems. Okay. Actually, we can think of it in terms of growth of some operators. Okay. All right.
So here by spectral statistics, you mean the BZS?
Yes.
Conjecture.
Yes.
But it's still a conjecture.
Yes. Yeah. So that's why actually I'm saying that it's not settled yet. Yeah. So, yeah. Actually, it's the most well known. Yeah. Since we are sort of any 100% good definition. This is the best. Okay. So let me try to explain this spectral statistics a little bit. Okay. So now I have come to the third point. Okay. Classical chaos. So I have explained this, why no chaos in a single degree of freedom system. And now I've come to quantum chaos, and I'll explain one of the diagnostics, which is spectral statistics. Okay. Oh, for spectral statistics, I think I plan to write on the board. Okay. Spectral statistics is actually very easy. Okay. So we have done quantization of simple harmonic oscillators, right? Quantization of particle in a whale. Okay. And as we know, for particle in a whale, we have seen that the energy is proportional to the quantum number square, right? So En is equal to n times some constant. Okay, some constant. Let me call it some k. Okay. So if we write this, if we plot this as a as an energy diagram, it will look like this, right? As the energy grows, okay, En, yeah, the first ground state will be something, and then the second ground state will look like this, and then the third ground state will be more bigger, right? Because it goes as n square. And similarly for a simple harmonic oscillator, okay, in a quadratic potential, as we know very well, the energy look like this, right? N plus half of h bar omega. So in this one, the spectrum look like this, right? Of course, in this one, okay, the spectrum will be equally spaced. The zero will be the n equal to 0 will be the ground state, half of h bar omega, right? This everyone know. And then this is the first excited state, this is the second excited state, and so on. Okay. So in this spectral statistics, what people do is that you analyze the difference of this energy gaps, okay, neighboring energy levels. Okay. So in this harmonic oscillator, the difference of the energy levels, let me call it delta En. It will be a constant, right? It will be nothing but h bar omega, right? So let's call this En plus 1 minus En, and it will be nothing but h bar omega, right? How about for this particle in a whale? It will be delta En will be equal to En plus 1 minus En, and it will be nothing but n plus 1 square minus n square, and then this constant. Okay, so what will it be? So it will be n square plus 2n plus 1 minus n square. Okay, so this n square will cancel, and we'll be left with this 2nk. So this energy gap, as I was saying, it keep increasing. Okay, all right. Now, for a quantum chaotic system, which we study using this spectral statistics, the conjecture, okay, as Professor Dilip was saying, the conjecture is that, and by the way, this is for a simple solvable system, okay, but for a more chaotic system, you can actually solve it for the double pendulum, okay. I asked one of my, project student to quantize, double pendulum oscillator, okay. And actually from here, you can do many things, okay. Even though this is a very simple system, actually you can calculate what are called, what I was saying, these complexities, okay, you can calculate, okay. So we are trying to do many things, okay. You can actually try to do many things, even for a simple system, okay. So, if you quantize this, what we found is that, by the way, this, as I was saying, is not exactly solvable, okay. So we have to solve it using a, computer, okay, numerically, okay. So, for using this spectral statistics language, what this BGS, okay, says is that this energy gap En, okay, it has a particular distribution, all right. So see, I'm writing here En, as a function of n, right. So if I plot, for example, for this one, if I plot this En as a function of n, what will it look like? It will look like simply this, right? Some delta function here. So this will be my delta En. What am I doing? What I want to draw is, let's draw delta En here, and let's draw n here, okay. Since this is independent of n, this will be, for all possible n, this will be here, all here, right? Okay, I'm not drawing it.
Just invert the axis first.
No, actually, this is finite, okay. N, okay. Yes, n changes. Actually, this is correct. Yeah, this is correct. Okay. And for this one, what will happen? En as a function of n, it will look like, it will be a straight line, right? It will be a straight line. Okay, with some, with some intercept and then some slope. For quantum chaotic system, this conjecture says that actually this En, it should look like this. Okay, this is called usually given the name Wigner distribution. Okay, all right, and for a classically quantum mechanically non-chaotic system, this En will look like a Poisson distribution.
The axis delta E should be on the y-axis.
Actually, I'm drawing the distribution now. Okay. Yeah, energy distribution now. Yeah. So yeah. So yes. Yeah, I should draw it more carefully. Okay. So what do you mean by distribution? Distribution is okay. It's saying that as you know, there's a distribution. For example, the distribution of the height of the people in this room. Okay. It will look somewhat like this, right? Some between, let's say, 5 feet to 6 feet or something. The distribution will look like somewhat like this, right? And this will be the number of person who have this much height, right? Right. So this, let's call it the height. And the number of person who have the height will be, start from, let's say, 5 feet or something, and then it will peak around 5.5, 5.7 around, and then it will start decreasing, right? So you plot the distribution of this, and that distribution will look like this for the chaotic system, and for the other one, non-chaotic system, it will look like a Poisson distribution. Okay, so that's the conjecture. Okay, by this. So this last part is actually slightly technical. Okay, but if you want to study, actually, you can study it in just 2-3 hours. Okay, you put in some, you just need your attention for 2-3 hours, and actually, this is very easy. Okay, so as I was saying, what you are studying is nothing but the energy gaps. Okay, what is the distribution of the energy gap? Okay. So with this, let me stop. Okay, and so I think I have covered my 3 points, which I started here. Yeah. Any question? Yeah.
So in classical chaos, we have this notion of classical chaos. We have this.
Okay.
We have this notion of sensitivity to initial conditions.
Uh-huh.
So how is it? Difficult in the case of quantum chaos?
Actually, it will take some time for me to cover it, and actually, I tried covering it in one of the talk here, Reese talk some 4 years ago. It has to do with this very, very hot topic right now, which is this out of time ordered correlation. Okay, it's a 4-point function. Okay, but it's out of time ordered. Okay, not time ordered. Okay, it's a 4-point function in general. Okay, so using that, it gives you some notion of sensitivity. Yeah.
And likewise, you will have some parameters that can.
Yes. Yeah, and actually, there has been a very, very famous conjecture, sort of conjecture, but it's widely agreed. Okay, that the quantum Lyapunov exponent, it will be bounded by beta to the power beta over some 2 or some factor. I have forgotten actually. 4 pi. Yeah. These are people work done by Maldacena, okay, Sankar and Stanford. Okay, Sankar and Stanford. Okay, Stanford. Okay, you can just type up. Okay, chaos bound. Okay, if you just Google chaos bound, okay, this paper will come up. Yeah, there is a notion of this Lyapunov exponent, and the people have been studying it. Okay, very, very, very intensely. Okay, in the last, this chaos bound paper is just come up 9 years ago. Okay, and it's a field of intense research. Okay, all the cutting edge research is done there. Many of the cutting edge research.
Because I just have one simple question,
Mm-hmm.
because I was not in the introductory part of the talk.
Uh-huh.
Can you just somehow try to bridge, the connections that the quantum technology where people are working now,
Mm-hmm.
the current state,
Mm-hmm.
how your quantum chaos is going to explain some of those, quantum technology? You are going in that way or different way? Or is it
So these are some of the applications. Okay, actually, Professor Dilip one application is in trying to explain high TC superconductor. Okay, so the most promising theory of high TC superconductor Actually, it's a quantum chaotic system. It's a strongly interacting high thesis book. They go by the name of strange metal. Yeah, it's a topic.
The reason I'm asking is that because you said that quantum chaos, the theory itself is quite not settled yet. Right?
Yes, yes, yes.
So when the theory itself is not settled yet, how people are trying to explain certain things, which is a chaotic system? That's what I'm asking.
I think it's very similar to how, for example, quantum mechanics arises, right? You know, quantum mechanics, people, Einstein always oppose it, but you know, it finally, as you accumulate more and more evidence, okay, you know, finally people come to some consensus, okay. So things are going like that. There is no like one paper, bang, and then yes. So it's not like one paper and bang, so this person gets very famous and this and that. Okay, it's not like that. Everything is. Yeah.
Let me add to that.
Yeah.
There are two aspects of quantum chaos. One is that, let's say that you have a classical system, which you know is chaotic, and then you quantize it.
Yes.
So
Yeah.
that is one way that we know for sure
Yeah.
that the quantum counterpart will be chaotic.
Yes.
So, for example, could be logistic maps, quantum logistic
Yes.
maps. The other aspect is that you have these quantum chaos that emerges out of a many body system.
Yes.
So what you have essentially been focusing on is, I think, more of a many body quantum chaos.
Yes. The final part. I use the definition for just single particles. Okay.
But
Yeah.
there are these two aspects.
Yes.
How to know that a system is indeed quantum chaotic.
Yeah.
One is that you have a classical system, which you know is chaotic.
Yes.
You quantize it, and we expect that it should be chaotic
Yes.
in the quantum domain.
Yeah.
And that can be verified using this DZS
Yes.
conjecture.
Yes.
The other aspect is that you have a quantum many-body system. We have no idea how the system will be
Yeah.
in terms of its dynamics.
Yeah.
But you look at the dynamics, you look at the spectral statistics, and you find that, yes, it does satisfy DZS.
Yeah.
But yes, as you are saying, in that context, it is difficult to understand.
Yeah.
There are many more.
Yes. But actually, even the first settled one that Professor Dilip was saying, I think there are some very esoteric examples which are classically chaotic. But if you quantize it, they are not chaotic. Okay. So
There are examples of
yeah. So there. So So it's a very, very hot topic. Okay. Actually, nothing is settled. Yeah. In that sense. Okay. But
that is also.
yeah.
So that's why I said
Yeah.
you have to check whether the system in the quantum domain is also chaotic
Yes,
by
yes.
doing this.
Yes.
DCS.
Yeah.
Otherwise,
Yeah.
you are absolutely right.
Any further question? Yes, please.
Let us consider the double pendulum
Uh-huh.
example.
Uh-huh.
Let's assume that we have a purely isolated double pendulum.
Uh-huh.
And if we do an experiment
Uh-huh.
and we will trace out different trajectories,
Yes.
suppose we record the trajectory
Uh-huh.
and if we repeat the experiment
Mm-hmm.
with the same initial condition,
So actually, chaos arises with this problem. How do you do the same thing? That's the problem.
but since the system is very simple, can we do the experiment with the same initial condition?
Let's say you do it, for example, actually the equation cannot be solved exactly. So let's say you use numerics, okay? You use double precision or single precision, whatever you use, okay? If you use the up to the decimal the same thing, then of course the computer will retrace all the calculation again. But if you make slight changes, okay, then things will go haywire.
Okay, no change.
Yeah. Yeah, actually, I can tell you more. Okay, actually, people have shown this. Okay, using binary computations. Binary computations, even systems which are chaotic. Okay, if you use the same binary, then you get the same result. Okay, so actually, people have done this, numerical experiments. Okay.
My question is,
Yeah.
suppose we hang the pendulum up to a certain height,
Uh-huh.
for example, say 5 centimeter,
Uh-huh.
and then we drop it,
Uh-huh.
and then it traces out a random trajectory.
Yes. Yes.
We recorded it through the computer.
Uh-huh.
So then if we repeat the same experiment with a 5 centimeter height,
Uh-huh.
my question is, will it trace out the same height?
If you use everything same, every binary same, okay, then it will trace out.
Then there will be no chaos.
But that's not the definition of chaos. Okay.
Since we recorded the first result,
Uh-huh.
then we can predict.
It's because the computer, whatever the computer doing, is a set of step which is very definite. Okay, so it will not give you chaos. Okay. I can tell you more. Okay, but It's the you should you should be careful about this sensitivity to initial condition. You should be very careful about this. Okay. But if you put in all the value, okay, up to all the mantissa, you call it the mantissa or significant digits, right? All same, okay. Then the computer will retrace it again.
Okay, you think about okay. No. So this question and answer is also very important. Since it is a quantum session, so I will narrate a story. I am a good storyteller about Dirac. When Professor Dirac gave a talk, someone says, I cannot follow your talk, something like that. And then the chairman asks Professor Dirac, would you like to answer? Professor Dirac kept silent and you answer, please. The chairman asked him. So Professor Dirac told him, it is a statement, not a question. It is a statement, not a question. So he never entertained the statement. So I'm just joking. So part of asking question is a part of learning. And I attended some international conference workshop. Special prizes were given at the end of the conference to those persons who give comment, who ask questions, who interact with the speaker. So some invisible judges try to pick out the audience, the participant, and at the end of the conference they were given special prize. The message is that the art of asking is a part of learning. Okay. So we encourage art of asking questions. Okay. Okay, thank you. So let us give some memento. It is the goal, so you can preserve.